Euler's method. Yeah, I'm not going to do the derivation, just give you what the update looks like. So here, you compute y at a half step. So a complete step is I plus 1, but you compute that at a half step plus delta x divided by 2 f of xi yi. So that's a half step. And then the full step, which is I plus 1, is yi plus delta x f of xi plus delta x divided by 2 comma yi plus half. So you want to remember both these formulas. So why this method? It turns out that can be shown using Taylor series that the truncation error is order of delta x cube. The total error is of the order delta x square. Okay, it's comparable to the Hume's method. Okay, I think I made an error last time in the notation. Well, the calling these names. So I said that this is the Runge-Kutta method. It's not the Runge-Kutta of order 2. Okay, that's not true. This one, the one which I wrote down, is actually, so this is the Hume's method. I incorrectly said it's Runge-Kutta of order 2. Turns out that the modified Euler is actually Runge-Kutta of order 2. Okay, that gets us to Runge-Kutta of order 4. It's a very popular method. It uses, so this one uses two function evaluations. By function evaluations, it needs to compute f twice. Okay, why is that a problem? Because when you have a physical system, you have a differential equation. That differential equation is, in this case, it was, the problem we solved was very simple. But if you have like a code, that differential equation might be, trying to, in FEM might be figuring out like meshing the whole, after you mesh the whole system, the elements, you might have to do a lot of computations to figure out what that f is. And so every time you call f, you need to do a lot of calculations. And so in those cases, you're worried about how many times I would have to call f. And so the fewer times you call f, the better it is, because less computations. But sometimes if you want accuracy, you need to do more computations. So here we have 2 evaluations of f in the modified, but Runge-Kutta uses 4 to give you a higher accuracy. So there's a trade-off. So Runge-Kutta of order. Oh my God. I seem to have lost everything. Now it closed. Oh, it's here. Okay, my bad. Thankfully, I didn't lose anything. Okay, let's look at Runge-Kutta of order 4. The update, I'll let the update first. I plus 1. Well, let me just write the individual steps first. K1 is delta x f of xi yi. K2 is delta x f of xi plus delta x divided by 2 yi plus k1 divided by 2. So k1 was computed earlier. K3 is delta x f of xi plus again delta x divided by 2 yi plus k2 divided by 2, where k2 was computed just one step above. And then finally k4 is delta x f xi plus delta x yi plus k3. Okay, so that's the case, but how do you use this? Well, yi plus 1 is yi plus 1/6 of k1 plus 2k2 plus 2k3 plus k4. Okay, so that is everything you need in order to update y based on Runge Kutta. The truncation error of this is truncation is of the order of delta x raised to 5, which makes it kind of accurate, and the total error is of the order of delta x raised to 4. Okay, so let's put all this into, yeah. Oh, why is it k3 divided by 2 here? It's not. It's not. It's y. Well, it comes from the derivation, so you need to basically put this in like a Taylor series expansion, and then having that the way it is gives you delta x raised to 5. If you have it as divided by 2, it will not be 5. So that derivation is kind of lengthy. Okay, so let's put this to practice. Let's solve the same problem we solved earlier, but use these methods and maybe compare them with what we had previously. So, example. Consider the ODE dy dx equals function of x comma y minus 3y. Okay, this is not a function of x, but in general, you can expect to be a function of x and y. Okay, so question is used. Missing something. And the initial condition is y0 equals 1. The question is using a step size of delta x equals 0.1. Compute the solution for x 0 to 1 using a modified Euler's equation and b Runge Kutta method of order 4. So by the way, I should have done this in the past. This equation, I intentionally took it because you can analytically solve for y. Okay, we'll do that first, so that we can compare. So this is not in the question, but we can analytically solve this. Analytical solution. So dy by dx equals minus 3y. How will you solve this? Well, you would move the y down. So separations of variables. So you club all the y's together, all the x's together. You would then integrate this. The limits are y0. So let's say that this is here y0 to y, and x will be from 0 to x. So we have log y, upper limit is y, lower limit is y0 equals minus x, upper limit is x, lower limit is 0. So log y minus log y0 is minus x plus 0. So it cancels. This can be written as log y divided by y0, right? Minus is can also be written as division, the way I've shown it there, equals minus x. And so the analytical solution is, this is the analytical solution. So now we have a good reference to check. So once we get an answer, we can actually plug in the value of y0, which is 1 here, x, whatever it is, 0, 0.1, and compute what y is. And then we can compare it against the other values we get from modified Euler and Runge Kutta. Let's do that in a bit. Okay, so that's the analytical solution. Modified Euler. So the way I like to start this is I would write the formula for modified Euler and then identify what sort of columns I need to generate in order to compute the answer. So the formula for modified Euler is yi plus half equals yi plus delta x divided by 2 f of xi yi, and the second formula is I plus 1 equals yi plus delta x f of xi plus delta x divided by 2, and then we need to do yi plus half. Yeah, let's identify what we are given and then identify what we need to compute. So delta x is 0.1. xi will be the lower limit, 0 plus I delta x, where I will go from 0, 1, 2, so on till 10. So xi will be something like 0, 0.1, 0.2, so on till 1, 0.9, and 1.0. Okay, what else are we given? We're given y0. y0 is 1, the initial condition. Okay, with that, I think we are all set. Okay. Now to evaluate the first part, we need this quantity. So let's just make a column for that. Delta x divided by 2 f of xi yi. Okay, so with that, we can compute yi plus half. It's just going to be the sum of this one and this one. So we note that. Now we can move on to the second part. We already have yi in the table. We need to compute this quantity. Let me call that something. We call that, let's say, dy. Okay, so just make it easy to not write a big formula there. And then once we have dy, you can see it's very clear that all I need to do is sum dy with y to get yi plus 1. So what remains now is to just populate this table. 0, 0.1, just start one at a time. So y, so when you put I equals 0, we have x of 0 is 0, y of 0 is 1. Delta x times delta x divided by 2, so something like 0.1 divided by 2. F of xi, this is minus 3y. So minus 3 times 1, right? So minus 0.15. Then we need to sum yi with this. So 1, so this should be a minus sign here. Minus 0.15. So 1 minus 0.15 is 0.85. That's what we get here. Okay, that takes care of this. Then we need to do this computation. So this is kind of a little bit more involved. So sub in the value for xi, which will be 0, delta x is 0.3, y plus half you already know. So it's actually not that hard. dy is going to be, okay, because it's just a function of y, it's kind of easy. So it's easy to see that this will be 0.1 times, this is minus 3y, right? So you need to put yi plus half. So you need to put 3 times this value. Sorry, my bad. This value, 3 times 0.85. Okay, question, do we have to do this? No, you don't have to do what I'm showing you here. It's really up to you. I just find it's more convenient to explain it when I have this columns and it's very clear where numbers are coming from. So it's not required. So I think I'm missing a sign somewhere. This should be minus 3y. So this should be a minus here. Oh, the analytical solution? No, well, for the analytical solution, there are many equations which do not have the analytical solution. So this one, I just chose it because there's an analytical solution and we can check, but you don't know the analytical solution. And that's the reason why we are even using numerical methods to solve it. Okay, so this is dy comes out to be minus 2.2550. Let me just write it on a new line. Okay. This also a new line, minus 0.15. I need some space for the analytical solution, so I'll just move this. Then we have yi plus 1, which is just summation of dy and yi. So 1 minus 0.2550, 0.7450. Okay, now question for you guys. If you have your calculator, can you try to compute the next line? So x is 0.1. For yi, you just have to copy this here. Now compute this, and this, and then I'll just give you the solutions for the rest. I did it offline. See if you can get it. I'll give you the answer in a bit. So try completing this blank. Everybody got it? No. 2235. I get half of that. Yeah, that's what I got. I think you might have missed this too. Check. Do you have this? I have it written down. Yeah. Oh, I see. Okay. So then we sum the two, this with this, and you get 0.6332. Then dy, we write that down, and then you can take on from there, 0.1. This is the step size. So I'm looking at this formula. F of this is minus 3 times whatever I got for this, 0.6332. So that comes out to be minus 0.19. And then yi plus 1 is, which is basically summation of dy and y plus y yi is 1450. So this would be 0.5550. Two 0.2, you'll copy this down as is, and then just keep continuing it. So just do it for 2 or 3 more. I'll give you the solution. Check with my solution, so you get the you sort of understand the logic. How do you get y exact? We just derived that. It is here, maybe no, here. Yes, the analytical solution is this. So all I need to do in the analytical solution is put y exact. I just put y0 equals 1, x is whatever x is. So we write it here. Xi. So I just computed it. Just make a sanity check. If you put x is 0, you should get 1, right? Yeah. Oh, y plus 1. So first you need to put xi equals. Okay, there's going to be a problem here if you put. This is my bad. This should be y exact I plus 1, right? This is, we're comparing against this. So x I plus 1. So let me just check my calculation here. 1 times exponential minus 9048. Okay, so here the value is 0.8187. You can see it's going way off. I think it's strange, 0.3679. Quickly check something. Y exact. Looks fine. Just it looks way off to me. You can see that if you compare 745 and 0.90, so the truncation error is delta x square. So delta x square. So you would expect an error of 0.1 square, approximately 0.01. I think that's strange. It's so much off, 0.15.
Exact. When you say I plus 1, you mean x I plus 1?
Yeah,
okay.
I plus 1. I put 0.1 here because xi plus 1 is this point. This is xi, right? So the next one.
Okay.
Yeah, but I'm not really convinced that this is the right answer. Look at how exact is different from y plus 1, and the error shouldn't be that large. I mean, I get the same error with Runge Kutta. Oh, I think I know what the problem is. What's the solution? I think I might have missed something. Hold on. That's the exact solution. Yes, I missed here. Nobody saw this. There's a glaring error here. What's the error? Got it? No. Just well, yeah, 3x. That will make a huge difference, obviously. So let's go and change that. Okay, all this is incorrect. Clearly, I used the wrong formula. Should have even taken the pains. So let me put it in my Octave solver and see what we get. Okay, much better. Okay, so here the what I get. 7408 5488 4066 0.3012 2231 1653 1225 10907 10672 0498. Okay, now it makes more sense, right? So they're not very off. So compare these two. I plus 1, yeah. You have to use I plus 1 because this is computing by I plus 1. So you need to put xi plus 1 formula. So one reason why you want to do this with the analytical problem is, and this is how debugging goes for anything. You write very complex code, you get answers, you submit it, you don't even care checking it. You don't get the right answers, things will fail, right? If in the real world. But having a problem whose solutions is known, and by checking your calculations to agree with that, gives you some confidence into the calculations. And then maybe if you have code which works for A, B, C, D, E, F problems whose solutions then you have some confidence at the quality of your code or quality of your calculations, and then you can move on to trying to apply in a scenario which you've never seen. And that's like the fundamental thing which unfortunately we don't really teach you here, but in the real world, you first do a calculations to check if whatever you do makes sense. So validation, and then you extend it to unknown scenarios. We have 8 minutes. Okay, so the next part is to try this on the Runge-Kutta method. So for that, let's write the formula down. So B so we have I plus 1, sorry, let me write K, the K's first. K1 is delta x f of xi yi. K2 is delta x divided by 2. Phi plus delta by 2 plus yi plus K1 divided by 2. K3 is delta x f of xi plus delta x by 2 yi plus k2 divided by 2, and k4 is delta x f of xi plus delta x yi plus k3. Rewrite this. K4 yi plus k3. And the update is y plus 1 equals yi plus 1/6 k1 plus 2k2 plus 2k3 plus k4. Okay, everything is now here copy pasted from the formulas I gave you. Nothing is new. So what you'll do is a very similar process, xi, yi. Okay, now what we need is k1, k2, k3, k4, right? So you just write k1, k2, k3, k4, and it's clear that then you can compute y plus 1 by using this formula, or if you wanted, you could also have a column for this sum. That's up to you. Okay, so 0, 1 is the first one. I put in the value for f of x comma y, so that now that you know how to do this, I just write it down for a few ones, minus 0.3, minus 0.25, 5, some space here, minus 0.2616, minus 0.2215, and y plus 1 is 0.7408. So you should compare this with your calculations, and you can just keep doing that. Then you do 0.1, copy this value here, compute k1, k2, k3, k4, k5 with, you should know that this is minus 3 yi. Okay, for here, since I had this question, a few people asked, this one you would put minus 3 yi plus k1 divided by 2, because that's what the formula says, right? You just have to sub in the value of y. So remember that, otherwise you'll get a calculation error, and so on for k3, k4. Okay, so what I'll do is I'll just, there's nothing really new about doing this calculation. It's the same way as before, maybe punching more numbers. I'm going to give you the solution, and then we'll compare it again, the exact value, and then we'll stop. Y0 e raised to minus 3xi plus 1. And then the values which fit in here are as follows. $7,408, $5,488. You can see that they're actually matching the value on the left side. 4066, 3012, 0.2231, 0.1653, 0.1225. It's almost like I'm copying that column down, but that's what you get if you put in the formula. 0907. Here it's slightly off. 0672. Oh, it's the same one. And then 0.04. So we have a perfect match up to 4 decimal places. Okay, so that you can see how powerful the method is. It gives you kind of good accuracy for up to 4 decimal. Of course, if you go 6, 8, then it will not give you accuracy.